maybe we can pass to the next talk, Brad.
Hi, sure. Can you hear me?
Yes, we can hear you.
All right, let me throw up my screen.
Yes. And in the meantime, we can leave all the questions to the end. So please, if you have any question, please use the Q&A section or just raise your hand and I will unmute yours. Okay,
right.
now we have the presentation of Brad. Thank you for being here. Please, all yours.
All right. Thank you very much. So you can see my slides, all right?
Yes.
Okay, great. Well, hello everyone. My name is Brad Theilman, and I am a postdoc at Sandia National Laboratories in the U.S. And I'm in cognitive and emergent computing, and my background is in neuroscience, but now I work on neuromorphic computing. And I'm happy to talk today about our work on decomposing spiking neural networks with what we call graphical neural activity threads. So being a neuroscientist, I'm sort of obsessed with spiking neural networks. And I believe spiking neural networks are on the frontier for AI research because we are surrounded by existence proofs that intelligent adaptive behavior emerges very efficiently from biological spiking networks. Artificial neural networks used in AI and spiking neural networks share historical motivations, but spiking neural networks operate very differently from their ANN counterparts. So this leads to the question, what, if anything, is special about spiking neural networks that allows for these capacities? The two fields that are most heavily pursuing the theory of spiking neural networks are, of course, computational neuroscience and neuromorphic computing. Each field has different ends, but to answer the question of what makes spiking neural networks special, they both require appropriate abstractions for spiking neural computation. And so the goal of this talk is to introduce a method for decomposing spiking neural networks that points towards a new kind of abstraction for spiking neural computation that complements existing approaches used in both of these fields. So I'd like to start with traditional approaches to decomposing spiking neural networks. Traditionally, we will take spiking data from a spiking neural network and subdivide it into small time bins or epochs and quantify the spikes that occur in each epoch. Here I have an example of a raster plot that illustrates the spiking activity of several neurons on the y-axis over time on the x-axis, with each tick mark corresponding to a spike. And spikes that co-occur within a time bin are used to form a sequence of high-dimensional vectors that live in a high-dimensional neural activity space. And the computation of the network is sort of abstracted as a trajectory in this high-dimensional space. And this is a very productive way to analyze spiking network activity, but it does have some issues that I'd like to point out. Sorry. The first is that these time bins are experimenter defined, and they're not intrinsic to the network or to the animal itself. And so this already introduces a sort of, perhaps you could say, a bias in our understanding of the spiking neural networks that's not actually part of the system itself. Furthermore, this state-to-state computation, when we think of spiking neural networks as being parallel architectures, the transition from one state vector to the next happens in parallel through the propagation of spikes to the network. But still, the effective computation is this serial sequence of activity vectors. And finally, it's known that both in biological and artificial neural networks exhibit tremendous amounts of variability. So if you apply the same stimulus or input to a spiking neural network, you're not likely to get the exact same spiking response out. And so this often implies that these state transitions are non-deterministic, and this complicates our analysis and sort of makes this picture of a nice high-dimensional trajectory a lot fuzzier. So those issues come out of decomposing spiking neural networks in this sort of vertical fashion by assigning spikes to time bins. And what I'd like to illustrate is perhaps an alternative way to go about decomposing the activity. So we know that the fundamental interaction on which spiking computation has to rest is the synaptic relation between neurons, because the appearance of a spike from a given neuron is caused by spikes from other neurons in the past. And so the question that we tried to answer was that, well, could we quantify this causal relationship between spikes in some meaningful way, and then use that to relate spikes that are perhaps causally related into groups that might form a sort of horizontal decomposition. And so the way that we went about doing that was we defined this quantity omega that we refer to as sort of a causal distance that depends on the time difference between pairs of spikes. And it's made up of three quantities. The first is, of course, the normalized weight between the neurons. So if two neurons are disconnected, this will be zero, and this quantity will always be zero. But otherwise, this is a measure of the connection strength between the neurons. Next, we have a term that is the Heaviside step function applied to the time difference between the spikes, along with the conduction delay. And so this enforces that a presynaptic spike has to occur at least one time or one conduction delay before a postsynaptic spike for that presynaptic spike to have a meaningful causal influence on the postsynaptic spike. And finally, we have an exponential term that applies an exponential decay with some time constant as a function of the separation in time between two spikes. So if two spikes are widely separated in time, the causal effect of the presynaptic spike on the postsynaptic spike decays. And so this is sort of an arbitrary, well, not arbitrary, but a formula that we came up with that captured our intuitions about what constitutes a meaningful causal relationship between spikes. And we wanted to use this quantity to try to decompose networks in this horizontal fashion by relating spikes that are causally related. So what I'm showing you here is a population spike raster from a simulated spiking neural network that was randomly initialized, but evolved under its own activity using spike timing dependent plasticity for a period of about 20 simulated minutes. And it has about 800 neurons in the network, 800 excitatory neurons and 200 inhibitory neurons. And what we did is we went through, and for each pair of spikes, we computed this quantity omega. What we then did was we thresholded this quantity omega by identifying pairs of spikes that had an omega value that was above some threshold. And I'll describe in more detail what the meaning of this threshold is in a minute. But using this threshold, we were able to build a directed graph on top of the spikes themselves by putting a directed edge between a presynaptic spike and a postsynaptic spike if the value of omega between those two spikes exceeded this threshold. And so this gives us a directed graph that lives on top of the spiking activity. What we found, which was really interesting to us, is that this graph naturally decomposes into disjoint connected components. So what I have here is that same graph, but now I'm coloring the edges of each disjoint component with a different color. And what we can see is that even though the original spike train didn't show very many patterns that were easily discernible by eye, we're able to extract these sequences of groups of spikes that are sort of bound together by their shared causal relatedness between the spikes, and importantly, are disjoint from each other. And we refer to these disjoint subgraphs of disjoint connected components of this activity graph as graphical neural activity threads, or NATs for short. So this is a kind of a zoomed in view of the NAT dynamics that we see in this example network. And I want to use it to point out a couple of features that we see that emerge from this view of looking at spiking neural activity. The first is that you can see that in any given period of time, there are multiple disjoint threads that are sort of simultaneously active. And remember that each color corresponds to a disjoint thread. So this means that there are spikes that are happening around the same time that are causally disconnected from each other. They don't share any causal past or future. And so I would like to argue that this indicates that these patterns of spikes belong to distinct computations, because if the spikes were part of the same computation, we would expect them to be causally related at some point in their timeline. And so also this also points out a contrast between a traditional time bin approach to analyzing neural activity, because we can see in these time bins, I've got these dotted lines representing 10 millisecond time bins, that there can be many spikes that belong to the same time bin, but belong to distinct threads. So this gives us a distinction between a time bin approach to decomposing spiking activity and then this thread-based approach. This is just another example of the transition between two threads, during the course of the network's spontaneously or self-driven activity, where we can see several spikes bound together into one thread that sort of dissipate, and then several candidate threads start to emerge, but then finally one sort of takes over and takes on the activity, carries it forward into the future. So one question that you might have about these threads is whether they are in some sense natural or not, or well-defined. I mean, how much of this graph structure that we're seeing is due to the artifacts of our particular way of quantifying the threads. And so we did a test to see, sort of how intrinsic these edges that we find are and how they depend on these parameters used in our analysis. So on the top here, I am illustrating the distribution of, in this case, the negative log of this omega quantity over all the pairs of spikes in the network. And this is for the empirical data that we obtained from our spiking neural network simulations. And you can see that it shows a very strong peak at small values. And because it's the negative log, small values correspond to large values of omega, so strongly related neurons, or strongly related spikes. When we shuffle the spikes in time and recompute this omega, that peak disappears, and we have this null distribution that we can use to compare against our empirical distribution. And this allows us to set a threshold for omega that extracts pairs of spikes that are strongly causally related. And this is what we use to define those edges. Now, you might be asking, because this quantity omega depends on things like this time constant, and the edges that we include depend on this threshold, how robust are these edges? Well, if we change this value of the time constant, then the effect is that it'll stretch or squeeze this graph out, but it won't actually change the shape of the distribution. So if we compare it against the null distribution, we find that the threshold will covary with the change in tau, and if we set it according to that covariance, then the edges that we include under a different tau will be the same as the edges that we included under our original tau. So in this sense, the edges that we include in the graph are independent of the parameters that we used in the analysis. And so this is why we argue that these threads are well defined by the network. So it's interesting that the network sort of naturally decomposes in this way, but what would be more interesting is if we had a way to identify if similar threads or even isomorphic threads were reappearing at different times in the network. And we came up with a relatively efficient way to find these reoccurrences using what's called the modular graph product. And I don't have time to go into the details, but the idea is that you can take two separate graphs and build a larger graph that's sort of like a Cartesian product, but a little bit more subtle, such that connected components of this larger graph correspond to isomorphic subgraphs in the original graphs. And so we can apply this to our activity graphs obtained from the spiking networks, and we can extract similar patterns of activity that occur at different points in time in the history of the spiking network. And we actually find quite a diversity of these shared subthreads that consist of different numbers of spikes. And the thing that I'd like to point out is that this doesn't rely on the precise spike timing. Instead, it relies on these causal relationships captured by the edges. So you can see that between the two isomorphic subthreads, the exact spike timings are not preserved, but the relative causal influence is preserved. And I'd like to argue that this makes more sense from a spiking neural network perspective this makes more sense as a way to define computations existing within spiking neural networks. So what we can do is that we can take our spiking activity and find these isomorphic subthreads embedded in larger activity threads, and we can use this to build a graph of threads. So each point in this graph on the right represents a NAT, or a graphical neural activity thread, and they are linked by an edge if they share a subthread, as illustrated by the shared black subthread in this example in here. And what we find is that the spiking neural networks sort of naturally cluster, these threads that we extract sort of naturally cluster into clusters that are related by shared subthreads, which is really interesting because what we can do is we can extract those clusters and pull them back to the original activity. And we find that in the evoked activity of a spiking network, here I have a spiking network that's being presented with a pattern of activity, we can find the same sequence of threads evoked by the input pattern, but sort of modulated on each trial. So even though it's not apparent by eye that the spikes in each of these blue regions are somewhat similar, our NAT analysis allows us to extract these shared subthreads in a way that is both flexible to the precise spike timing. It doesn't require precise spike timing, and also robust to noise, because since we're looking at subthreads, shared subthreads, what's happening around those shared subthreads is not important for identifying this relationship as much. So I'd like to conclude by just saying that NATs, or graphical neural activity threads, provide a decomposition of spiking activity that is naturally adapted to the dynamics of spiking networks. In particular, NATs unite the spiking activity and the connectivity into a single mathematical structure, which we think is natural for spiking networks. And the fact that NATs do not rely on precise spike timing shows that NATs balance flexibility and rigidity and are composable. We can extract similar subthreads across different threads that appear at different times, showing that spiking neural networks have this repertoire of threads that they can kind of rearrange and recombine in interesting ways. And these are desirable qualities that we would like in any abstraction of spiking computation. So for more information, we do have a preprint available here that describes this analysis in much more detail and also includes some more thoughts. But basically, our future work is trying to understand how the connectivity structure of a spiking network leads to the repertoire of NATs that it is able to produce. And if we understand that, then we might be able to understand how to link specific threads to particular computations. And then we can understand through the compositionality of these threads how to compose these compositions to get more complicated behavior out of spiking neural networks. So that's all I have for now, and I'd be happy to take any questions.
Great, thanks for the presentation. I don't know if there's any question from any of the attendees or the panelists. I don't know if the panelists have questions. Well, if not, well, we can leave the questions to the end.
All right.
Thank you very much. Thank you.